What if I told you? Most high-power inverter systems don't fail because they aren't strong enough, but because they were designed like small systems scaled up, instead of completely rethinking how high-power energy actually behaves. High-power inverter setups are a different world compared to small portable systems or basic RV installations. Once you move beyond a few kilowatts, everything changes. Not just the size of the inverter, but the way electricity flows, the way heat builds up, the way batteries discharge, and even the way safety must be handled. Because at high power levels, you are no longer dealing with appliances. You are dealing with energy infrastructure. And infrastructure has rules that cannot be ignored. At the core of any high-power inverter setup is the same principle. Convert DC power from a battery bank into usable AC power. But when power levels rise above 3 kilowatts, 5 kilowatts, 10 kilowatts, or even higher, the system stops behaving like a simple device and starts behaving like a network. Everything becomes amplified. Small inefficiencies become major losses. Thin cables become heat sources. Weak batteries collapse under load. Poor design choices become system failures. So high-power systems are not just about bigger components. They are about controlled energy flow at scale. The first major element is the inverter itself, and high-power inverters are fundamentally different from small ones. They are designed with higher internal thermal capacity, stronger switching components, advanced cooling systems, and higher surge tolerance. But even the best inverter cannot fix a poorly designed system around it. Because the inverter is not the source of power, it is just the processor. Everything depends on what feeds it. That brings us to the most important foundation, the battery bank. At high power levels, batteries are the fuel tank and engine supply line combined. If the battery bank is undersized, you get voltage collapse, inverter shutdowns, and reduced system lifespan. This is why high-power systems almost always use large lithium battery banks and high-discharge BMS systems. Stability matters more than raw capacity. Now let's talk voltage. 5 kilowatts at 12 volts can exceed 400 amps. 5 kilowatts at 48 volts is around 100 amps. This difference is massive. That is why serious setups move toward 48-volt systems. Higher voltage reduces current, which reduces heat, cable thickness, and energy loss. In high-power design, voltage is a survival strategy. Every connection must handle industrial levels of current. Extremely thick cables, short runs, and bus bars for centralized distribution are essential. At this level, even a slightly loose connection creates a heat point that can escalate into a fire. Now let's move to surge handling. Motors and VAC systems can surge 2 to 7 times their normal load. A 3 kilowatts load might briefly demand 10 kilowatts. High-power inverters must react instantly, maintaining stable voltage during these spikes. Heat is the fastest killer of electronics. Robust cooling systems, high-speed fans, and large heat sinks are mandatory. Every degree of excess temperature reduces efficiency. Safety design at high power is not optional, it's structural. Proper fusing, DC breakers, and emergency shutoffs are your 3 layers of protection. A single short circuit at this level releases enormous energy instantly. Finally, monitoring allows prevention instead of reaction. Real-time data on battery voltage, current, and temperature is required. A high-power system is not just a device setup, it is an engineered balance. It's not about having the strongest inverter. It's about every component supporting every other component under extreme conditions. Because at high power, nothing fails alone. Everything fails together if the design is wrong. If you want more deep practical breakdowns like this, subscribe to Off Grid Life Tech.